Great to have Meghal Gupta here in our Young Research Seminar series. Meghal's a student at Berkeley working with Venkat Goswami, and she's been working on streaming algorithms and error correcting codes. And actually, also it's great to collaborate with her on a project with Naren on learning objective functions from pairwise comparisons, roughly. So things like Google Maps, and Google Maps suggests a couple routes to you, and you pick one, or maybe you pick something totally different, and then you're trying to learn about you. Anyway, that was really great. And today she's going to talk about, optimal quantile estimation for streams. So take it away.
Thank you. Thanks for the introduction. Okay, yeah, so as Albert said, I am going to talk today about optimal quantile estimation for streams. This is like joint work with Mihir and Hong Shun, both of whom are also grad students at Berkeley. Okay, so the first thing I'm going to do is start by defining the problem of quantile estimation. The basic idea is like you receive a stream of numbers and your goal is to estimate the median or the 99th percentile or some other percentile of the elements. More precisely, you receive n elements. All these n elements are in the range 1 through u for some like specified universe size u. And your goal is to be able to estimate quantiles or percentiles of the stream. Your goal is to do this while storing as little memory as possible throughout the stream. So like, you could trivially do this if you just remembered all of the n elements throughout the entire time, but the goal is to do significantly less memory. So the thing that we're going to be measuring our algorithm by is like how much memory are you using throughout the algorithm, and the goal of the algorithm is to be able to, at the end of the stream, answer these like percentile quantile queries. So I'll say a couple things about the parameters. Like I said, right now n was specified beforehand. That's not really a necessary thing, but it's just easier to formalize with. It's just easier to like state things with that for the sake of the talk. And also, I say that we're only answering quantile queries at the end of the stream, but really you could be getting them throughout the stream as well. It's just easier to focus on like how you would answer them at the end of the stream and like the same idea. I think the last thing is like the universe size u. So the universe size u having to be specified is like a little bit of a tricky thing. Like there's lower bounds against having an algorithm like ours if you replace like the concept of integers with just, okay, actually I won't get into this too much, but like the universe size u is a universe size, needing to know the universe size u beforehand is not quite necessary, but you do need to know beforehand that there are like all numbers with like fixed precision, and sort of like your dependence on u will instead be your dependence on like, or like your dependence on log u, which is the number of bits required to specify a number, will instead be the dependence on like the longest like element you ever needed to specify if you try to get around u. So yeah, I'm not going to get into that fully, but for the sake of this talk, n is known beforehand, u is some fixed universe size parameter, and we're only going to need to answer quantile queries at the end of the stream. So precisely what is like a percentile query? So you receive a rank r between 1 through n, and your goal is to output an element of x whose rank, i.e. the number of elements less than x, is between r minus epsilon n and r plus epsilon n, where epsilon is some specified parameter. You can also like consider the reverse version of this problem, which turns out to be equivalent, which is you receive an element x of 1 through u and want to output its rank in the stream up to additive error epsilon n. So you receive some element x and you want to approximately output how many elements are less than it, up to some additive error epsilon n. So that it'll be sort of like easier to analyze with regards to the second definition. So throughout the talk, we're going to be focusing on like you receive an element x and your goal is to output how many elements are less than x, roughly. Okay, so any questions about this statement of the problem? We'll do an example in a second.
When do you know R in this process? When do you know R in the like? Does the algorithm know it beforehand? Does it work for every R?
So the algorithm is given R only at the end, but actually turns out to be equivalent if you know R beforehand. It's not actually any easier if you know R beforehand. Okay, great. So let's do an example. So in this example, so the stream is displayed here, and the goal is to estimate the rank of 3, i.e. how many elements roughly are less than 3. So the correct answer to that is 4. And and like a functional algorithm would output 4 plus minus epsilon n. So if epsilon were 0.2 in this case, then you would be allowed to output like 4 plus minus 1. But like if epsilon were like 0.01, then because there's only 6 elements in the stream, you have to output 4 exactly. Seem pretty reasonable? Does the model make sense?
So would an algorithm for this kind of thing, if you're allowed to be randomized, be let me just try to just remember a random subset of order 1 over epsilon points and kind of, I mean, they'll, on average, ish, then you give me something and I just see where it is relative to the small number I'm remembering. Would that be an algorithm that would be reasonable randomized?
Yeah, I think that one will take like log 1 over delta, where delta is your failure probability times like 1 over epsilon, roughly. Yeah, so that's like, for example, a way to do quantile estimation. And you can actually, like, for the randomized thing, for the thing that you were saying, like the naive way would be, I think log 1 over delta over epsilon squared might be the naive for that, but you can get that down to log 1 over delta over epsilon via some tricks that are like sort of described in future slides. But yeah, like the most naive way to do quantile estimation is to remember all the elements. The second thing you could do if you do like randomized, if you're okay with randomized, is you can just remember some subset of the elements. The amount of elements you have to remember is like log 1 over delta over epsilon squared, and you could just remember those and then use those to estimate the quantiles as well. Those are in fact two ways to do quantile estimation. Okay, so I guess I'll quickly talk about some applications of quantile estimation. So one is estimating system reliability, for example. Like if you want to know the 99th percentile latency of your system, you like want to know the 99th percentile quantile. This is a great example of something where R is actually known beforehand, but like it doesn't actually help to know R beforehand. Another thing is like user analytics for websites and online content. Like if you don't want to know the median time like a user spends watching a video, that's like a quantile problem. Or like the amount of time that a typical user spends on like the home screen of some app, that's like also a quantile estimation problem, like, or the median user, let's say. And there are companies that like exist basically to like do these sorts of like user analytics basically like as efficiently as possible. Yeah, there are a number of libraries for quantile sketches, and like, I don't know, I have no idea whether our algorithm would actually be more efficient in practice, I think, than like some of the existing things out there. I think there's a lot of cool existing things out there, and like, even though asymptotically they're kind of worse, they're only asymptotically worse by so little that even if the constants in our algorithm are pretty small, like I think they're probably only like 5 or 10, it's sort of unclear to me if the saving is large enough even then. Yeah, I'll talk a little bit more at the end, I think, on how, on like practical considerations for this thing, but yeah, anyway. So, okay, so let me talk about like the history of algorithms for quantiles. So like, as I said before, like all our algorithms for quantile estimation are going to be measured in basically how much space they take. You can also measure them in how much time they take, but like this trade-off is generally pretty clear. Like I think we're going to focus on space for this talk, but you can like sort of translate this entire talk to time instead, to sort of also be a sensible talk. Yeah, so we're going to measure our space in units of words. Words are just log n plus log u bits. It just makes things easier to write down. It doesn't really mean anything in particular. So the first quantile sketch I want to draw your attention to is the Q digest sketch. So the Q digest sketch is in the same model as the problem that like I introduced earlier, and it takes epsilon inverse times log u words of memory. This will actually be the algorithm that our algorithm is based off of. And yeah, basically our algorithm is just a modification of this one. It's like definitely the closest related one to ours. Another interesting quantile sketch is the GK sketch. This one takes epsilon, or the Greenwald and Khanna sketch. This one takes epsilon inverse log n bits of memory, epsilon inverse log n words of memory. And this has the additional, so this is like not comparable to Q digest. It's not like clearly bigger or smaller. I think probably for most practical purposes it's pretty similar in terms of like asymptotics, because like n and u probably don't differ by more than a polynomial. I mean, I guess I say probably, but maybe there are regimes where people care about cases where n and u are like vastly different, and then one of them these is significantly better than the other. Anyway, so the GK sketch is comparison-based. What comparison-based means is instead of getting the elements as like integers that you can like see and understand, you just get like black boxes that you can compare to each other. And when I say like one word of memory, I'm saying like storing one of these units of like comparator of like object that I can compare to other objects. That's like 1 unit of memory. So instead of one word being log n plus log u bits, it's one object plus log n bits. So under this model, the GK sketch is optimal. But as long as you receive your numbers as like real numbers with fixed precision like floating point numbers, like their lower bound goes away. You don't even have to know u beforehand. Like their lower bound disappears as soon as you like actually think of your numbers as integers. It's just like a theoretical model that people built because I guess like it makes analysis of various like streaming algorithm problems like make more sense sometimes. Yeah. So anyway, so those are the two like most well-known deterministic algorithms for quantile sketching. The third algorithm that I want to draw attention to is the KLL sketch, which ties into what Avram just brought up. The KLL sketch is randomized. It also satisfies the comparison-based property, which is like stronger than not satisfying it. And this one achieves epsilon inverse log 1 over delta. Like a naive way to achieve something basically like KLL is basically to use like GK or QDigest on top of what Avram said, like sample like log 1 over delta over epsilon squared points and then apply one of these other algorithms. But like this algorithm actually gets around like lower order terms. Like I think that procedure will give you some like log 1 over epsilon sorts of things. And I think the point of this result is basically to get something that's like exactly correct up to like multiplicative or even like additive log 1 over epsilon factors. Yeah?
Delta is the failure probability?
Delta is failure probability, yeah, sorry. So like I guess if
so what is the dependence on delta for the other ones?
so the other ones are deterministic. There's everything else is deterministic. Yeah, so I guess if delta is 2 to the n or something, then this is like sort of comparable to the others. But if you are okay with significantly smaller failure probability, like it's probably reasonable to say failure probability should be at least polynomial because like you might want to answer queries after like quantile queries after every element and you want to get them right. I don't know, maybe you don't even need that guarantee, but if you want like poly n guarantee, this is significantly better than the other algorithms. Yeah, so anyway, the main purpose of this talk is to get an algorithm that achieves epsilon inverse words of memory. So in bits, that would be epsilon inverse times log n plus log u bits. This is like the best possible thing you can do, both randomized and deterministic. Or sorry. I take back what I said. This is the best possible thing you can do deterministic. It is not the best possible thing you can do randomized. In randomized, you can replace the log n in the bits part of this, or sorry, in the word part of this. You can replace the log n with like log n, because you could do some sort of approximate counting. But in the deterministic setting, this is the best you can do, and this does beat out the previous best randomized algorithm as well, though of KLL. Yeah, so now I'm going to quickly go on a digression about the lower bound. So I say this is optimal. So I guess precisely what I'm saying when this is optimal is that there's a lower bound that matches this upper bound of epsilon inverse log u plus epsilon inverse log n bits. So the epsilon inverse log u is like super easy to show. It turns out, or like it's not too hard to see why. Basically, you receive if you have an algorithm that receives epsilon n copies of each of 1 over epsilon elements, you have no choice but to remember them all. So there's 1 over epsilon distinct elements, and you receive each one like epsilon n times. You need to be able to basically, like if you ask all the quantile queries in order, you need to be able to recover all of them. So there's nothing you can do to get around epsilon inverse times log u. There's a log epsilon u here because like you can, if you're more careful, that's what the true bound is, but it like doesn't really matter. However, there wasn't really a known. Okay, I guess like when we were trying to write this paper, we were like, okay, so everyone in the folklore, like everyone in the literature said there's an obvious lower bound of O of epsilon inverse. Well, like no one wrote it down, so we were a little bit confused. We were like, okay, we don't actually know how to prove this epsilon inverse log n lower bound. Like we tried for like 10 minutes, we couldn't solve it. We were like, okay, is this actually non-trivial or like is there some silly argument that we're missing? So we couldn't solve it, and then we looked at the literature, we couldn't find it anywhere. We emailed people, like nobody seemed to know this lower bound that apparently was just folklore. And like, if anyone's heard of the Misery-Gries algorithm, this like the lower bound for this and that are like the exact same thing. Like they actually map to each other. And like no one could tell us a lower bound for that either, even though everyone says that it's optimal.
What is the other thing called?
Miser agrees. I think it's like top k counting or something. In a stream, like you want to find the approximate top k elements. Yeah, so there's this like lower bound that's been stated for various streaming algorithms in the literature, and we have no idea how to prove it. Eventually, we concluded it was just actually a hard problem that like no one had like specified or solved, and then like it ended up being a SOTA paper in 2024 after we told people about the problem. Yeah, it's a pretty cool proof. So if you like want to check out like a cool proof at any point, you should look at that. Yeah, so anyway, for the rest of the talk, I'm basically just gonna describe our algorithm. So I'm gonna start by, I guess to outline what I'm gonna be doing, I'm gonna start by describing the Q-digest algorithm. That's probably gonna actually take most of the time, because actually it's probably gonna take like half of the remaining time of the talk to describe the Q-digest algorithm. And then after that, I'll like describe the modifications we made in order to make it like, slightly more efficient.
I'm confused. I think there is still a gap, right? Like your result is 1 over epsilon log n plus log u, and here you have epsilon inside the logs.
Yeah, I guess, okay, I wasn't careful on the previous slide, but actually our result is is actually matching this exact thing. I guess the reason I wasn't super careful was it's an additive log 1 over epsilon. I think you're right that, you're definitely right that I should have, that like, this should be stated more precisely. It's not precisely as written. It's not stated precisely as written. And like, yeah, the correct truth is to like keep the epsilon inside the logs as well. Okay, yeah, and then so I'm gonna first talk about Q-digest, and then I'm gonna talk about like our modifications.
Sorry, I missed the beginning of your talk, but in this model, are we allowed to query it at all values of n we want, or there's a fixed value of n?
We're just talking about making a single query at the end, but it's like sort of easy to modify it. You can basically do the algorithm for like all scales of n or something, and it turns out that you can not do this. You can like not gain a factor of log n by doing this somehow. But yeah, we're just going to try to make a single query at the end. I was going to say one more thing that I forgot. Okay, I guess I'll just start talking about the Q-digest sketch then. Okay, so just to recall our goal, the goal of the Q-digest sketch is we're going to receive some numbers x1 through xn, and then we're going to, like at the end of the stream, we want to be able to output like, we want to receive a query x and be able to output like the rank of the element x. Okay, so I'll start by describing just like how this Q-digest works, like how we insert elements into our like data structure, and then I'll talk about like why it works and the space complexity. But first, I'm just going to talk about like what it does. So the way that an insertion works, so if we insert an element into our stream, then we insert it into the tree, into the topmost node whose interval contains it, that is not yet at capacity. So every node is going to have some capacity alpha. Alpha will be set to epsilon n over log u, but that's not super important for now. And the way the algorithm works is it inserts every single element we receive into some node. So it's sort of grouped into that node. And then, let's do an example of that. So we have a stream that's specified here, and let's say alpha equals 2. So the capacity of every node is 2. So the first element we receive is 3. The topmost node that like can absorb that element is this node. So we put x1 equals 3 in there, then we put x2 equals 2 into here, and now x3 equals 2 doesn't fit into the top node anymore. So now like it spills into one of the children, and then we keep doing this. Does like the way that this algorithm works make sense? Yeah, so so far we haven't really described why this is like actually improving anything, like we're still storing all of the elements. But the point is, at each node we're only going to store the number of elements it has, so sometimes we're just like grouping our elements into groups, and then for each group we only need to store how many elements were in that group, and we don't actually care about the exact identities of the elements in that group. It should not necessarily be clear yet why this works. Okay, so I guess to see why this works, let's figure out how we're answering a rank query x. So let's say we get a query x equals 3, and I'm going to claim the algorithm for answering that query is we take all like nodes that are left of like the path leading down to x equals 3, and then we return the total count on all of those nodes. Right, so let's figure out why this works. So first of all, every element that was inserted into one of these blue nodes was definitely less than 3, because the intervals like all only contain elements less than 3. So definitely all of these elements were less than 3. Similarly, like if you look at the green nodes, like there's only one green node here, but really it's like all of the things that are like to the right of the path containing x equals 3, all of those are definitely more than 3. The only things that we're unsure about are the path leading up to 3. Those things, like those elements that were inserted there, those could be more or greater or less than 3. We don't know. But the point is that's how we like chose our capacity alpha. There's log U ancestors, so the total error is at most alpha log U, and alpha was epsilon n over log U, as you can see here. So the total like additive error is going to be epsilon n. Yeah. So does it make sense why this like algorithm works? I haven't yet gotten to the space complexity of this algorithm, but maybe I'll let it sink in for like a minute, and like if anyone has any questions on why this works.
Can you repeat which element goes to which node again?
Yes. Okay, so we first get the element 3. The top node is, so I guess when we get the element 3, the path that it could go into is this path right here, right? The path that it gets inserted into is this path. So the top node, the topmost node of that path is still like still non-full, right? So then we can put it into that. And then similarly, the next element also gets put into that because the topmost node is still non-full. Now the next element 2, we try to insert it into this path. But the topmost node is now full, so we have to insert it into the like node below it.
Why the left one on that in that case?
Because the left interval contains is 1, 2, so it's the one that contains the element 2. Like we're inserting the element x3 equals 2.
Okay. Oh, so those intervals existed prior to the stream.
Yeah, the intervals existed prior to the stream, and the property that we're going to need to satisfy is that if an element is inserted into the node, into some node, then that element was inside the interval.
So U is 4 here in this case?
Yeah, U is 4 in this case.
Construct the nodes.
It's just a binary tree. So like let's say U is like 2 to the k, then the topmost interval is 1 to 2 to the k. The left one is 1 to 2 to the k minus 1, and then the other half of that. Like basically you just split it into you start with like everything, and then you just split into 2s into like the first half and second half.
So if all the elements are identical, which gives a trivial answer, but for this algorithm, do you have enough space to store all the elements?
Right, so I guess in that case, okay, when I said the capacity of every node was 2, that's true for everything except the bottom layer. So the bottom layer has infinite capacity, and then when you do the error analysis here, like only these nodes actually count towards the error, so it doesn't matter that the bottom node has like infinite capacity. But that's a good question. Yeah, so the statement of the algorithm makes sense now? And does like the reason that it works make sense? So the reason it works again is because like we have these blue and green nodes. The blue nodes are like definitely less, the green nodes are definitely more. The only uncertainty is on the red nodes. And the red nodes, there's only log U of them, and there can't be too many elements per node, so that's how we get our error bound. Great. So now the thing we need to analyze is space complexity. So what do we need to store? We need to store the list of all of the non-empty nodes and their counts. So the number of non-empty nodes is approximately n over alpha. You can show that if the capacity is alpha and you do this like push-up strategy where you always like try to fill like the higher nodes before you like bleed into lower nodes, that the number of nodes will always be at most like O of n over alpha. It's just a thing you can show. And so that's approximately epsilon inverse log U. The list of nodes only takes one bit per node to store. Yeah, so for each of these nodes that we discussed in the previous step, you only need 1 bit per node to store it, because like you just need to store the structure of the tree, which is like a binary tree, so it just takes 1 bit per node. You can like show that a binary tree takes 1 bit per node to store, like to specify the structure of. Right. And then the final thing that we need to store is we need to store the count per node. So each of these nodes has a capacity, which we only need to store once, but then like there are going to be a lot of nodes that are like that aren't at capacity yet, right? They have some count that's associated to them that isn't like alpha. And in order to store this value, we need like log alpha, which is approximately going to be O of log n bits per node. So this gives a total storage of epsilon inverse log u times log n bits. Does that make sense? We have like epsilon inverse log u non-empty nodes, and at each of them we need to store a count. At least at the leaves of this tree we need to store a count, and the number of leaves in a tree is approximately just the number of total nodes in a binary tree. So the target that we were going for was epsilon inverse log u plus epsilon inverse log n bits, right? So basically the goal of our algorithm is going to, I erased the wrong thing. I meant to say that we're going to try to, the goal of our algorithm is to reduce the space needed to store the counts. I crossed out the wrong thing. I meant to cross out the O of log n bits per node in the counts. So instead of trying to store these counts in O of log n bits, we're going to try to like do some trickery to store these counts in like O of 1 bits instead. So does like the sort of setup make sense? Basically the next few slides where I describe our algorithm are just going to focus on like how we get rid of these counts and we store like quote approximate counts that only take O of 1 bits of memory instead. And specifically the description I'm going to give in the following slides, the counts will take, I think, O of log 1 over epsilon bits each, but like you can actually make it O of 1, but I'm not going to get into that. Anyway, so the goal now is going to be to try to store these counts efficiently. So, like, in some sense, what do we want to do? We want to do approximate counting, right? We want to store, like, approximate counts of these nodes because then they can be stored much more efficiently. The problem with approximate counting, first of all, it's not deterministic, and I promise you a deterministic algorithm. And even if we allow randomness, I think, like, using a Morse counter will, I think, give you worse bounds than KLL, but maybe it's, like, similar bounds to KLL with some, like, additional log 1 over epsilon factors. I'm not sure. I think it should give you worse bounds, actually, but I don't quote me on that. So we need to store approximate counts in some way, but we can't, we can't just like directly do counting deterministically and approximately. That sort of data structure doesn't exist and like is not possible. And even if we allowed randomness, like, first of all, Morse counter has a factor of log n, and also like, it's not clear that it gives like great bounds anyway. But somehow we're still going to be accomplishing this goal. So, I guess to phrase to structure like what we're trying to do in a slightly different way, we're going to be processing our insertions in batches of size alpha, and so we have this tree over here. We have some full nodes, which are like the grayed out nodes, and then we have some nodes, or some full or like not at least partially filled nodes, and then we have some nodes below them, which in this case I've listed as V1 through V4, and we're going to take a batch of elements of size alpha, and after each batch we're going to increment the counts of Vi approximately correctly. Okay, so I guess to rephrase like the problem, to rephrase our goal here, we're gonna look at a batch of size alpha elements. I'm sort of just saying that we're going to do this arbitrarily. There's not really much justification I'm giving for why we're going to look at a batch of size alpha rather than just one specific element. And at the end of the batch of size alpha, our goal will be to increment V1 through V4 by some amount that's like approximately the correct amount. So the correct amount to increment each of these. So if we weren't doing any sort of approximate counting, what we could do is compute the value C1 through C4 for how much we actually wanted to increment each of V1 through V4, and then we could push up in case, like, let's say this node over here wasn't actually full, we could then, like, push up in order to fill it and like, satisfy the properties of our QDigest algorithm. So I guess what I'm saying is if we wanted to get exact count, if we wanted to, like, get exact count still, what we could do is receive a batch of size alpha, figure out how many elements were supposed to go into V1, V2, V3, and V4, and then push up to fill the nodes that are, like, above V1, V2, V3, and V4. And that would still satisfy the properties of our QDigest algorithm. But what we actually want now is we want to obtain approximate counts, Ci prime, which are close to these true counts Ci. So like we're going to increment these counters by C1, C2, C3, and C4 respectively, but we actually only need to do it by some approximate values, C1 prime, C2 prime, C3 prime, and C4 prime. So what do I need? I guess the thing that we really need to specify here is what do we mean by approximate? Like, what does it mean for a count to be approximately correct? So whenever we perform a rank query, so I guess like really this comes down to like like when we perform a rank query, we need it to be basically correct. So when we perform a rank query, we add up C1 through CK for some K. Like we're sort of assuming that everything else so far is like correct enough, so I'm not like accounting for the error from these top nodes here. I'm just accounting from the error from like V1, V2, and V3. So if we look at that error, we need the approximation to C1 plus ... CK for each K to be accurate within epsilon alpha. So in particular, we need to choose C1 prime through CK prime so that all these prefix sums, C1 through CI, are accurate within epsilon alpha. I accidentally flashed the next thing, but does anyone see where this is going? So I guess this actually turns out to just be a quantile sketch. So why is it just a quantile sketch? We're basically looking at the universe of elements, V1 through V4, and we're trying to, for each of them, compute roughly how many elements, like when we're saying we want to approximate the prefix sum C1 through CI, we're just trying to say roughly how many elements were less than VI that we received. That's like basically the question we're asking, right? So we're basically just doing a quantile sketch here. And each of these counts is allowed to be off by epsilon alpha, which is exactly like the condition for a quantile sketch. So this is just a quantile sketch. In particular, what we need to do now is we need to perform a quantile sketch on V1 through V4. Earlier, we need to perform a quantile sketch on our entire universe. Now we're just performing a quantile sketch on the leaves of this tree that we've formed so far. So I guess pictorially, we sort of like take this tree and we sort of do this shift, and we're just like doing quantiles again on like this new tree. So the thing that we've gained here is that the universe size is much smaller. Like previously, our universe size was U, right? But now our universe size is just the number of like leaves in this tree. And in particular, okay, maybe this is, so the universe size is just the number of leaves in this tree, which is log U. So I guess before I go into the space analysis more carefully, let me like sort of like clean up exactly what we're doing. Yeah.
So these VIs are intervals, right?
Yeah, the VIs are intervals.
So what does it mean that like you, like in the next figure,
Here?
like, what is like VI through V4? Like what does that mean?
It means the union of the intervals VI and V2, or V1 and V2. So V1 through V4 will mean the union of V1, V2, V3, and V4. V1 comma V2 is the union of V1 and V2. That is probably the better way to write this slide, but yeah, it's just like the union.
I have a question. So you create a sketch, a quantile sketch for the leaves of rank alpha. Why do you pick alpha to be epsilon n over log U?
So the reason that we need batches of size alpha is you want to make sure that during the process of insertions, the reason you can do this is because you want to make sure V1 through V4 don't overflow during this process. Otherwise, then this does, I guess at the end of the day, we're going to come back to our bigger tree and update it. And if V1 through V4 overflow, then we don't know which tile to put the things into. That's why alpha is the most
the size of, okay, that's how you pick it, so it's going to balance out.
We basically pick alpha to be this, and it turns out to be the best parameter choice. Yeah.
Now I'm confused about that. So say all the elements should have been put into V1, then wouldn't that cause the one above it to overflow? Because you might have alpha plus 1.
So at the end of the day, we're going to compute some quantities, some counts like C1 through C4, right? And all these quantities C1 through C4 are going to satisfy the property that they're less than alpha, right?
Yeah.
Because the total amount is less than alpha. So then we could just make V1 alpha.
I see. Okay.
V1 has 0. I guess the point is so right now V1 through V4 all have 0 in them, which means you can never need to push down. You could need to push up if this node is not yet full, but pushing up is a thing that you can do that loses specificity, not gains it, right?
Yeah.
But pushing down is not legal. So that's why alpha is the biggest you can make your batches.
So I guess there's the batch size, but in the original, before you went to this part, the alpha, I mean, sometimes that's the largest alpha you can get so that your error rate is only epsilon n, right? And I guess if alpha were smaller, you'd have more nodes being used, and so that's bad, right?
Wait, no, if alpha were smaller, you'd be okay.
But in the original alpha, right,
yeah.
then you'd have more nodes being used, and you'd have too much memory. Is that
Yes.
in the Q? I forgot the name.
Q digest.
Yeah, the Q digest, right? So
Yeah. I think
that's-
I think what you're saying here is this O of n over alpha
Mm.
would be bigger if alpha.
Yeah,
were
that'll
smaller.
be too large, and so you want alpha to be big for that to be small. But as alpha gets larger, then you're losing alpha log u in that path. Is that right?
Yeah, that's exactly
So
correct.
that's how you solve for alpha, basically.
Yeah. Like the number of nodes in the tree is n over alpha, so you want to make sure so that's like an upper bound on the space, or like you want to balance that with like making sure that. So I guess like the thing you need to be true is that the error along any given path is at most epsilon n, and you also want alpha to be big because you want n over alpha to be as small as possible. So yeah.
The tree that you're showing on the slide, is that what corresponds to the alpha elements you process? Like, is that an intermediate thing that, like, I don't understand how those alpha elements that you processed correspond to this tree.
The tree that's over here right now. So I guess so far if we've processed alpha elements, I'm claiming that they've all gone into these three nodes over here. That's how I'm illustrating this slide. So these three grayed out nodes, they've all gone into there. This top one here must be full. The second one here must be full. This one is not necessarily full, but it's like has at least positive capacity. It has at least positive number of elements in it.
And this is independent of what has happened in your stream so far. Like, this tree is just constructed looking at those alpha things that you processed.
No, this tree is constructed using those previous elements so far. Like this tree is constructed from the previous elements. We have not inserted our alpha elements yet. Yeah, and the only thing we remember about the previous stream is like these three nodes of the tree. We don't remember like anything else about this tree.
So I guess you've seen at least 3 alpha so far. Otherwise, you wouldn't have 3 nodes.
I guess you've seen at least 2 alpha plus 1.
Okay, yeah.
But yeah. I guess. Okay, so I guess since we've gone through this, so I guess the main idea of the thing was like we're gonna process our insertions in batches of size n prime, which we're currently setting to alpha, and our goal is to obtain approximate counts from on a smaller Q digest of v1 through v4. So let's do the parameters a little bit now. So I guess the main point of the parameters, I'm not sure how useful it is to read all of them, but the main point of the parameters here is that we're only storing on these leaves of like the main Q digest tree, we're not storing counts anymore. We're just storing approximate counts, and in particular, like there are only like 1 over epsilon increments for each count because we're approximating each count up to like it's near like we're approximating counts up to like 0, alpha, epsilon alpha, 2 epsilon alpha, so on. Like we're approximating to the nearest like epsilon alpha for the prefix sums. So each count only takes like 1 over epsilon, log 1 over epsilon bits to specify. Using this, the thing where we're actually doing the count is like in our recursive Q digest tree. So like in our second layer of the Q digest tree, there we're doing like actual Q digest. So so the second tree where we're doing our actual Q digest, that we have to do like the actual parameters of Q digest, and that has log u. That tree will have like log u nodes, right, or like log u over epsilon nodes, because that was like the parameters of Q digest. Like, I guess the point. Sorry, maybe let me restart what I was trying to say. Okay, so when we did this, how do we calculate the parameters now? So we made a new Q digest sketch where the universe is just like the number of leaves in our initial Q digest sketch. This is log u over epsilon universe size now, and so like the space usage of this like new Q digest, this like inner Q digest we have here, that's going to be like log of the new universe size times log n, and log of the new universe size is just log u. So basically, the new inner Q digest will only take log u times log n all over epsilon space, because like if you just plug in the parameters of Q digest, that's what happens, and so like that's how we get this epsilon inverse log n times log u bits for the inner Q digest. And then the outer Q digest, we need like log epsilon inverse bits per node, as I said earlier. So like in total, this will give us like about O tilde of epsilon inverse log u words. So does that generally make sense? I think I got a little bit, like, I explained the parameters poorly, so let me know if anything wasn't clear. Yeah, anyway, so the main idea for like getting optimal space is just recurse this construction. Like we had this new tree on which we were trying to do QDigest. Why don't we just like apply our algorithm again? Because we claim our algorithm's like doing better than QDigest, right? So you just do this like log star u times, and I guess if you do this log star u times, you'll lose like error epsilon every time. So you'll need to set epsilon to epsilon over log star u. So you would get a log star u, but actually if you make epsilon vary, you can like get around that and you can get like the correct. You can just make things
That
converge.
removes completely the log+logU?
Hmm?
That completely removes the log+logU in the previous one?
So if you recurse the QDigest, I think directly you'll get log star u, because when you take log u, you like you log it again. Yeah, so you'll get log star u, but the thing is each tree gets smaller. So because each tree gets so much smaller, like the space actually converges. Even though there's log star u layers, like the sizes converge, so actually like the space usage is not that high. The main problem you'll have is that the epsilon, so the space usage converges easily. The main issue that you'll have is that the epsilons like add between layers. So you have to, so like naively you would have to set epsilon equal to epsilon over log star u, but then you would gain a log star u factor in the algorithm as well from that. And so like what you actually want to do is like vary the epsilons so that like things converge properly. And then you can get O epsilon inverse words using this, and this will, like as I've described it, this will contain some like polylog epsilon inverse terms, which are like a little bit more annoying to get rid of, but you can get rid of them too. And like I guess a couple of points I'll bring up here is that like the first one is like the way I describe the algorithm, you have to specify your, when you go from like the second layer to the first layer, you need like what log 1 over epsilon bits to specify like the count at a node. Even though now you don't need log alpha bits, you do still need log 1 over epsilon, and you only want O of 1, so you really just are only actually able to tell if a node is empty or full. You literally cannot tell anything else from your sketch. Yeah, there's like a few points that I don't really actually care that much about going into for now. Okay, so I guess in terms of practical considerations, that like basically concludes the like discussion of the algorithm. But considering like onto practical considerations, the main algorithm that's currently used in practice is KLL. KLL uses O of epsilon inverse log 1 over delta words. So KLL is like pretty good. It's only off from our algorithm by log 1 over delta. If delta is like small, if delta is like not that small, I guess, like there's really no hope for our algorithm being better, probably. I think the thing though is like our algorithm actually doesn't have terrible constants. So like there wasn't actually, like our algorithm is not actually that complicated, does not invoke any like strong theorems, so like it doesn't actually have like horrible constants. Like there's nothing, if you solve out for things, there's no constants that end up actually being like horrible.
Does it mean that this sketch is deterministic if you have log 1 over log?
I think I meant to say randomized.
Okay.
Yeah. Actually, I honestly don't know what I intended to write here.
Probably you mean your own algorithm.
Oh, that's probably what I meant to write,
What
yeah.
is it?
She mean that this refers to her algorithm, like the
Yeah, I think that this is the new algorithm is deterministic.
Okay.
I mean, I don't know how much I believe those things. Like, I think randomized algorithms are probably fine. You can also turn our algorithm into a randomized algorithm. Like, if you think about it, the only place the log n came in was like once we get to our like lowest level of the QDigest, then we need to actually deterministically like store all the elements or like do a like deterministic sort of like interval storing thing. And there, like, you need to store counts, but you can actually just store approximate counts there too. So you can like convert our algorithm to like replace all the log n's in our algorithm with like log n if you like allow it to be randomized. And then like, maybe then like the log 1 over delta factor will be relevant. I guess like the reason it's like possible that it will never be better than KLL is because log 1 over delta is pretty small. But at the same time, it's not like our algorithm has horrible constants. Like it's actually possible it just beats out KLL on like constant factors. And it's like different, so it's worth trying. I don't really know too much about like how to do a lot of this implementation in practice because I think they're almost certainly close enough that if you implement either one badly, it will lose to the other one. So like I think in order to get a real test of this, it would need to be implemented well. There's like a database called like Apache Sketches or something where like KLL is implemented, and like I'm super interested in seeing if like this algorithm could be implemented well enough to like beat out KLL in that setting. And yeah, I have no idea. There's potential reasons that it could do badly, but there's potential reasons the constants are just not that high. Yeah?
I was just wondering, like, if instead somebody says that can you sketch a rough histogram, you don't accrue errors across the different quantiles, right? Like, if I understand correctly, KLL would accrue errors across the different quantiles because this error is for one particular quantile query.
I don't think it accrues errors, no.
It doesn't?
No, I don't think either one will accrue errors.
So yours is deterministic, so there is no chance of accruing error. But even case, okay, that delta is really saying that it would be the error probability of answering all the quantiles correctly.
I guess as long as like delta is at least 1 over n, that should be true. Otherwise, yeah, it would be like the max error. The max error is actually, I guess, a little bit higher, right? But I guess, yeah, so I think, okay, I guess what you're saying is like, what is the max error? And yeah, I agree that you probably need delta to be at least less than like 1 over poly n in order to get like some reasonable guarantee for like the histogram. But again, like log n factors aren't obviously that big. Like log n is probably like, like 5 or something, like at most. So like, it's like very unclear to me, I guess, if like the factor of 5 matters that much compared to the other constants, but also maybe it does. Like maybe the other constants in both our algorithm and KL are just not that high. So yeah, I don't know if it'll work better in practice. I think it would be cool to see someone try. I don't know how to implement things well enough to like be the one to try. And yeah, I guess that's the end of my talk.
Other questions? Are there other kinds? I guess so. This is this quantile estimation. I'm trying to, I guess there's a bunch of problems that are all like that. Right? Well, yes, you mentioned like top K. Are there some like similar kinds of problems that seem to take a lot more space, or where does this kind of fit?
I don't know about ones that take a lot more space. I feel like I only know about ones that also don't take much space. Most statistics, I guess like L2 norm estimation is another very like common one that people discuss. Like, I mean, a lot of statistics are super easy, like mean, I guess, is super easy. L2 estimation is not like quite as easy, but yeah. I mean, I guess all the like LP estimations are also pretty classical ones, but like I think those are also reasonably efficient too. Like I think everything is sort of like in the log scale of efficiency, at least to approximate. I don't really know of any that are not. Maybe there are, I mean, there probably are.
Actually, do you know, so here's a question. One kind of thing you might imagine is the query is going to be 2 elements. And I want to know approximately how much stuff was between those 2. So you could sort of answer that up to this add of epsilon n. But that might give a boring answer if, I want to know, were these like adjacent? Or, like I might like,
right, so you
hope to get some relative.
You want the answer to depend on D, not on
how far they actually were. Like maybe they really were only a couple of things in the stream between them.
That's interesting. So I think something similar to that is quantile with insertion and deletion. And I know that maybe it's equivalent, I'm not sure, but there's a model for quantiles with insertion and deletion where you want the error to depend on the number of elements that are currently in the tree. So in that case, you could imagine like inserting all your elements, deleting all the things less, and inserting. I guess it's not quite the same because you don't know which elements to delete. So it's not quite the same, but it's like vaguely related. And that can be done sort of in the like polylog like regime as well. But I don't think that algorithm will give an algorithm for what you're describing. Because I think you actually need to remove the exact values for that. You need to know the exact values you want to remove.